Welcome back. Today we're embarking on the ultimate level-up journey through a topic that can honestly make or break your JEE rankings: circular motion. We all know the sheer stress of memorizing these mechanics, but whether you're targeting JEE Main or aiming to conquer Advanced, mastering this is absolutely non-negotiable. We're going to break down the complexities, decode those formulas, and set you up for maximum scores. So, let's get right into it.
But hey, before we start crunching numbers, let's think about a real-world physics puzzle. Ever wondered why a stone tied to a string stays perfectly in its circular path, or why a heavy, fast-moving car doesn't just skid right off the road when taking a super sharp turn? Well, hold on to that thought, because mastering the mechanics in today's explainer is going to reveal exactly how the universe pulls the strings to make that happen.
Here's our roadmap for today's explainer. First, the core engine, linear and angular. Second, the invisible force. Third, 2D navigation on banked roads. Fourth, the final boss, vertical motion. And finally, avoiding common traps. Section 1. Core engine, linear and angular. Initiating level 1. Before we can solve anything complex, we first need to translate our straight-line physics into the rotating, spinning world of circles.
Notice how perfectly this bridges those two worlds. Every angular quantity has a linear counterpart, and they're connected simply by the radius r. Your linear velocity, v, is literally just r times angular velocity, omega. And your tangential acceleration, a sub t, is just r times angular acceleration, alpha. Seriously, burn these into your memory, because this mathematical bridge pops up in almost every single JEE question on this topic.
All right, let's bust our very first common misconception. People hear uniform circular motion and immediately think, oh, uniform speed means zero acceleration. Yeah, no. Walk through this logical cascade with me for a second. Even if the speed remains completely constant, the direction of the object is continuously changing, right? Because velocity is a vector, a change in direction means the velocity itself is changing. And if velocity changes, acceleration absolutely must exist. Specifically, a centripetal acceleration equal to v squared over r.
Section 2. The invisible force. Moving right along to level 2. Now that we've got the motion down, we need to explore the forces actually pulling the strings and causing that acceleration.
Okay, let's dive into this because I see so many students lose marks here. Acceleration requires force, right? We call the force required for circular motion centripetal force, which is calculated as mv squared over r. But listen closely to this. Centripetal force is not a brand new magical entity. You're not going to find a centripetal force generator out in nature. It is always provided by an existing force.
Let's look at exactly what I mean. If you're analyzing a satellite orbiting Earth, gravity steps up to act as the centripetal force. A stone on a string? Well, that's tension doing the job. A car turning on a flat road? That's friction. The golden rule for your free body diagrams is just this: always resolve your existing forces toward the center of the circle. That net center-seeking force? That is your mv squared over r. Section 3. 2D navigation, banked roads. Let's level up to horizontal mechanics and apply what we just learned about forces to cars navigating flat and tilted curves.
Think about it. If a road is perfectly flat, the maximum safe turning speed depends entirely on friction. Specifically, Vmax equals the square root of mu times r times g. But let's be real. Friction is completely unpredictable. What if it rains? What if someone spilled oil on the road? To engineer a much safer turn, we bank or tilt the road at an angle theta. By doing this, we essentially force the horizontal component of the car's normal force to point directly toward the center of the curve. Suddenly, we don't have to rely on friction at all.
The absolutely crucial takeaway here is this frictionless speed condition, v equals the square root of r times g times tan theta. At this exact speed, the vehicle will cruise around the curve smoothly without requiring a single ounce of lateral friction. It's a massive game changer and a favorite formula of the JEE examiners for sure.
Section 4. The final boss, vertical motion. All right, we're leaving flat ground behind and entering the notoriously tricky 3D vertical loops, where gravity is constantly changing the rules of the game.
Think of a roller coaster or swinging a bucket of water upside down. Gravity is now fighting you at the top and helping you at the bottom. This means the tension in your string, or the normal force on your tracks, is constantly fluctuating. At the bottom of the loop, tension is at its absolute maximum, since it has to support both the weight mg and provide the required centripetal force. But at the top, tension hits its minimum. In fact, in the critical condition to just barely complete the circle, tension drops all the way down to zero.
Energy conservation is what powerfully links these two extremes together.
Let's move to the math and see how this builds into our most critical results. If tension is 0 at the top, the minimum speed required to just cross that highest point is the square root of g times r. Applying conservation of energy down to the lowest point gives us a required minimum bottom speed of the square root of 5gr. Listen, these two absolute minimums are extremely important, high-yield results directly tested on the JEE Advanced. Literally do not enter the exam hall without them.
Section 5. Avoiding common traps. We're entering the final phase now. You know the concepts, you know the math, so let's review the ultimate do not do this checklist to save those precious exam marks. Let's rapid fire through these mythbusters. Trap 1, drawing centripetal force as a brand new arrow on your free body diagram. Seriously, don't do it. Trap 2, thinking uniform motion has 0 acceleration. It absolutely has radial acceleration. Trap 3, calling velocity constant in a circle. The speed might be constant, yeah, but the vector is continuously rotating. And trap 4, using centrifugal force from the ground's perspective. Centrifugal force is a pseudo-force. It does not exist when you're observing from an inertial, non-accelerating frame.
If you remember absolutely nothing else from our explainer today, burn this foundational mantra into your brain. In any circular path, direction changes. Because direction changes, velocity changes. And because velocity changes, acceleration exists. Always. It's really that simple.
Well, we've covered the mechanics, the formulas, and the traps. But let's bring it all back to reality. We know gravity acts as the centripetal force for objects in space, giving us an orbital speed of v equals the square root of big G times big M over r. So here's a thought to leave you with. Based on the altitude of the International Space Station, how brutally fast is gravity forcing it to whip around the Earth right now? Grab a pen, plug in the radius, and calculate it for yourself. Keep practicing, stay focused, and I'll catch you in the next
वीडियोस बनाने हैं फिल्मोरा है ना।